Nah, physics for free and such. So we'll just do definitions of the basic vocabulary, the basic concepts, and see if we can find the little points of disagreement. Little things that aren't consistent with evidence in terms of statements that can be made is generalizations. So, kind of in the idea of this is what I think a book should be, is just redefining the definitions. The definitions always have a word in them that says, well, what does that mean? Like bits. And what does this mean? And what does that mean? What is, and you just can do that forever almost in a way of tightening up the vocabulary and showing the relationship between the concepts. So, I don't have all the words in here, just the basic ones: magnetism, gravity, force we'll start with, just because I figure that's where you should start. And unfortunately, no matter where you start in the circle, there's a place where, ooh, it's a circle, and so, it's you have to kind of go in. Once you have the circle, it all makes sense. But as you're making the circle, it doesn't make sense. It just looks like you're turning for some stupid reason, for no good reason. That kind of thing. So the first step requires you to suspend a little bit of disbelief, if that's what you need to do, to recognize, okay, what if I say that is true? And then you can move on to the next steps, and you see how the last step fits to the first step, and it all fits. The definitions work. So, all right, what is a force? So this word used all the time. You force the square peg into the round hole. That's not really the same word. Okay, so we're going to use a technical definition, and the technical definition would be about the stuff that's basically moving the speed of light. The little force, involved in gravity, magnetism, charge, and parts of electricity. So the force would be those little tiny things like photons, that like radio waves, like lots of stuff. So it can be waving, it can be raying. So those are words also that I have to put in here, just as they're apparently necessary. So the idea is that this force is that stuff. So let's just read what I wrote instead of saying what I'm saying. Elemental bits of momentum. So they're the smallest little things in the universe, and they apparently have this unkillable thing called momentum. Wherever their energy goes, that is their ability to move from point A to point B to point C to point D, that you can't get rid of. You can't kill the movement. You can't just make it go away. And I would argue that it's basically exchanged in the sense that it never dies, because yes, you exchange one bit for another bit, technically or factually. That yeah, so there's you end up going into words like trapped and all this kind of stuff, and but you really can't draw a picture until you have enough of a definition. If I just say little bits of momentum, well, that doesn't say anything much, except the point is that there's stuff, you could argue, that isn't going anywhere, and there's stuff that is going somewhere at the speed of light. So there's this stuff going the speed of light, and then there's other stuff that isn't going the speed of light, and I would argue that this stuff is inside of that stuff, frankly, and it's just trapped. It's doing this, or it's doing this, over and over, or it's doing this circle thing. So those are the only differences. And so this bit can make an exchange with this and cause one of these things to leave in some other direction, something like that, or in the same direction. And that's force. Force is this. Little bits of momentum. And that's how we kind of see the universe. They have a word, quantum, to sort of describe the fact that that is the elemental thing. And anyway, So absorbed through exchange by electrons and protons. So you sort of have to go to electrons and protons, right? You actually have to have some understanding of what they are. And they have what's called charge. And there's these two kinds, the proton and the electron. And the idea is that the proton and the electron don't have native, identity. That what they do is they capture some of this stuff, like trillions of years ago or whatever, and there's force inside of them, okay, doing stuff, in the traps, doing the square thing or the back and forth thing or whatever, and they have a net velocity in the universe. They're tending to move, and the next moment they will move in some direction, and it can be any direction. If you froze the universe, they would have the next, when you unfroze it, they would be moving in a direction, but that direction could be changing every 1/1,000,000th of a second, because they move basically based on what forces, little bits coming from other places in the universe, other protons and electrons hit them, and when those things hit them, they move. But the key point is they move, and they move because of this stuff. This stuff decides where they move. So the more force there is on one side, the more photons you hit something that will move in the direction you're hitting it with the energy. And it'll just move a lot slower because it has to carry whatever all this extra stuff is that's in here going around in circles. So these are electrons and protons are essentially little reservoirs of these little force bits. And so the key thing that I'm saying is it's like a little universe in there, in the sense that there's a bunch of little stuff taking paths where the paths end up complementing each other, and they're stuck in there. They can't get out. And not until a little new bit flies in and makes the exchange. And the exchange will basically be as a piece of momentum going, say, this way, will be exchanged. So this one will go in, this one will come out, and then the overall net condition of this electron, in this case, will end up having a little bit of movement in the direction of the force it exchanged. Should be enough for this moment. So I could say the elemental bits of momentum. So for the etherists out there, their idea is that something creates a wave that comes off of here, and clearly by Maxwell's equations and Maxwell's drawings, what's coming off of here are rays. Okay, little bits of momentum in discrete paths, and they create the inverse square law, because they're in three dimensions. In 3 dimensions, they're spreading. They're separating this way and they're separating that way because they come from a tiny point in space and go to a big place in space. So that fits Einstein's convergence, and that can also fit in ether theory if you just understand that the little bits in the ether are pathways. Okay, you could say there's a bunch of this little ether crap. This is why I just don't think ether is necessary. So you put these particles in all this random locations, and even if you put them in strict geometry, you're going to be in trouble. The point is there's no good straight line here to get anywhere with a vibration. The vibration's going to get broken. And again, we know that these things don't land as waves. I mean, a single photon goes one path. It doesn't do all this waving stuff and then land as a wave somewhere. Well, I'm way off the... It doesn't land as a wave anywhere. It lands as one little point, one spot, one little tiny place it lands. So this idea of wave is just incoherent to the facts. It's another reason just to forget about this ether garbage stuff. I mean, mush. It's rays, 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 rays. So I guess I have to emphasize that point. It's rays of force. Like I said, but if you want to force it to be an ether, you can. You could just say that the ether's already pressurized, though. That the bits, the particles that make up your ether, they aren't just sitting in a position. They themselves have a momentum. They're moving in a direction. Okay, and you can say that your ether perturbation just changes a direction. So instead of this bit moving whatever that way, it moves some other way because you perturbated it, and somehow they communicate between these force bits. Again, there's just I can't make an argument for that just because I think it's fundamentally flawed because the force bits don't interact with each other. But anyway, in any way that you would notice, you'd be able to see because of kinetics. A pure kinetic reaction, I've done this so many times, is indistinguishable. A pure kinetic reflection doesn't give you anything more than what the universe would look like. So if two things hit each other and reflect, it's exactly the same as the universe if they never hit each other, if they missed each other. You can't see that, but whatever. I've drawn it. It's it's just a fact. So, and clearly the elemental universe doesn't have any room for heat or sharing energy or something like that. It can't. It all has to come out of the. You have to conserve the energy, and so there's just no choice. It's the pool table on steroids or whatever. So if you take the pool table and really get rid of all the spin of the ball, get rid of all the slowness of the transfers and all that stuff, and you make it an instant, in terms of how the force is transferred, it's going to be like Newton's cradle. It's going to be, what goes in is going to come out, and it's just going to be different people are moving the different ways. So two balls hit each other. One starts going the way the other one was going. The other one goes the way the first one was going. It's that simple. Anyway, all right, absorbed through exchange by electrons and protons. I think I kind of covered that, but the idea would be that these are like boats, and the force, little bits of force, are like rowers. They jump in the boat, they change the overall disposition, and they eject somebody going exactly the opposite way, and the object now has a tendency to move in the new direction. So no conservation law has been violated. It's just that this is a type of battery, and you're just changing the disposition of the battery, which is perfectly legal, by exchanging two forces, taking one guy out who had a black shirt on and putting a guy there who has a red shirt or whatever. I mean, you're just exchanging directions by exchanging forces, bits of force. All right, what do force bits do? And what properties do force bits? That should be bits. Thank you very much. Have. Okay, so they move the speed of light when not trapped. They're still moving the speed of light when they're in a trap, obviously, but they're just not going anywhere. So they don't move in terms of change their location. Until they are released from the trap. So the idea would be is when they're inside of an electron, they're inside the electron in this trap, and they just can't get out. Or this trap. They're just going back and forth and back and forth and back and forth. And so there's, they're stuck in there. That's it. That's it. So although they're moving the speed of light, they're not moving in this direction or this direction or this direction. They're not getting anywhere or going anywhere. They're just stuck. And that's all they are. And at any one moment, their identity is changed based on which way they're going, of course. But that exchange only happens with the external universe. They only reflect because they hit something on the outside and reflect. But the point is that the progress of this location in space doesn't change. The form of it doesn't change. until something has changed in it. Some exchange happens that changes the direction one of these idiots is going. So these idiots are all going some way. They're all rowing in a direction. And the external force has to change the disposition of that. So by having more force on one side than the other side, and you're making these exchanges, well, we'll put 2 on this side. Well, if you make 2 exchanges going this way and you make 3 going this way, you can understand that now this hunk of space has changed. It went from being, having an imbalance in this direction to having an imbalance in this direction. Its direction changes, but this moves much, much slower, all right, than much slower than the force bit that hit it. So this force bit that was going the speed of light doesn't get where it was going. It was going somewhere. It doesn't get there, kind of clearly. And something else is going to get hit with this reflection. Anyway, all right. Next. They create a field that fills the universe. So these bits of force, we know they exist in the sense of this, like I said, whatever you want to call them, these waves of force, whatever. In the sense that there's this cosmic background radiation we already know about coming from all directions in space in somewhat equal proportions. They show these new images now that have gradations, but the gradations are 0.00000, tiny percent differences in the amount of energy, not big differences, tiny percentage. So tiny that you could argue that the margin of error is what the differences are created by. But basically the universe is full of pressure, full of this stuff, and it's moving in all kinds of directions, but any one object in the universe is only going to pay attention to the stuff interacting with it, and that's going to look like pressure from all locations. So I'm getting hit by radiation from all locations in the universe. They all have their guns pointed at me, and they're all shooting me with photons. Now, they're shooting everybody. They're shooting all over the place. But the point is, from my perspective, it's going to feel like pressure. And that's the nature of the universe. It's this word, pressure. So it's another key word that I probably should highlight. So when I say they create a field that fills the universe, now we have this word field, another important word. So I'm basically arguing field, okay, is made of something. It's not a field of nothing. It's not a field of whatever. It's a field of real stuff. The universe is made of this stuff, and you can change how much you can bias it by bending things, okay, by taking stuff that was going out, bending things, and you bend something else that was going this way, and you bend some more. You can create parts of the field that are imbalanced. That means there's more of these little force bits going this way in one part of the universe, and in some other part of the universe, way over here, there's a bunch of that stuff going that way to equal it out. Oh, you can't see that. Over here, then, there's a big hunk going that way. But it all equals out. But you're just talking about in certain places in the universe, I can make more of it or less of it. In a certain direction. I can change how much of one direction is somewhere. By putting some in an electron and making the electron move in one direction, I know the field has an equal balance somewhere else. Either there's more swimmers going that way somewhere, or there's another electron somewhere going the opposite direction. Kind of like the entanglement argument. A more rational description of the entanglement argument. Okay, so understand that when you say field, it's a field of soldiers, and they're doing something. They're all moving in a direction. And if you're you can be in the field, and all the soldiers can be going in directions that don't bother you. None of them are heading for you. Or you can be in the field and they're all heading for you. Just depends on what's in the field. But there's always soldiers. You can't eliminate the soldiers. You can just bias the fields. So the field can be, your part of the universe, okay, can have, this, soldiers all going this way, and then some other part of the universe will have that, and that, and that. they'll have that bias. So these are conserved, all right, but in any one location in space, there's no conservation in the sense that there's a clear bias in this location, and a clear bias in that location. And that means the stuff in those locations are going to get hit by more soldiers this way than that way. Or, women at the shopping mall at the big sale, and there's a big crowd, and they're going to get pushed into the store, whether you want to go shopping or not. Yeah. I think I'll take a little break just for the fun of it, and have a drink and smoke and such. Be back soon. Yeah, I'm back. So it's important to emphasize that the point I was trying to make or getting to was the fact is the field's always there. There's always the same number of soldiers, and it just what changes is how many are going one way or the other way. And if you're in balance, you just don't notice it. If as many are pushing you this way as they're pushing you that way, you just stay where you are and you say, there's no force acting on me. Well, there is a force acting on you, it's just that it's balanced. So when gravity happens, all we're really saying is the field is imbalanced. Okay, there's no such thing as gravity per se, the force of gravity. No, there's just a change in the sense that there's more going this way and less going this way. And you just change the proportions of which way you're getting pushed. So you're just looking for a change in the field. So fields are really important as a word just because it's changes in the field that cause you to move, that cause things to move. And the fields are local. Local to the atom, local to your big universe. There's fields inside the fields, inside the fields, inside the fields, inside the fields. And they all have they're either balanced or imbalanced. Now we notice when they're imbalanced because that causes matter to move, and we notice when matter moves, and that's essentially all there is. But the same amount of stuff was interacting. It's interacting in different proportions. All right, so that pressurizes the universe. So the obvious point is that this is all just about pressure, and you're sitting in a location, and there's either more stuff hitting you from one direction or less stuff hitting you from this direction, then you're going to go that way. And that's happening in all three dimensions all the time, and so your real vector is going to be something like that. But regardless, the point is that you can do the math and figure out where you're going. How big a change when you change one rower in the boat, how big a change that makes in the overall direction of the boat, the net direction. Okay. So we're still on the force bits, and so this is a definition of what a force bit is. They exist in two types, electron force and proton force. So this is where, I say it's trivially complicated, but it just takes such a step of imagination. But yes, there's this thing, it's a reality in the universe, this whole plus and minus thing. It's a real phenomenon. The fact that protons and electrons are different is one of the facts that makes the whole thing work. That they react different to the field. And so what you need to understand is there is electrons and protons, and there's also complementarily two forces that behave differently when they hit these two objects, and it's an inverse relationship. So what black energy does in protons, which is deflect, red energy does that with electrons. It deflects, and nothing changes except this is going this way and it wasn't before. Nothing changes in terms of what you can visually what you need to account for. The interaction ends up with this being the byproduct. Everything else pretty much stays the same. And then when the red force hits the proton, it reflects. okay, in the sense that it switches identities. It takes a rower going that way and throws him free, and this rower takes a seat in the boat and becomes part of the momentum of the proton. And so the result is an action happens here, and there'll be another action here that's a consequence of this exchange. It isn't created directly by the exchange. It's because this has the capacity to make exchanges. So momentum isn't, people have this idea that you just hit something. You hit something with a hammer. You take your hammer out and you whack something with a hammer, and this just goes. Well, it doesn't just go. Things don't just go. They have to absorb something to go. So you absorb force. You can't just go. You have to absorb the condition of go. So the wrench that I throw into space, let's say, and the wrench that I just let go of. So the two wrenches are different. One's moving with a velocity of 30 or 40 miles an hour, and the other wrench is just sitting here. Well, those two wrenches are elementally different. The one that's moving has different rowers in its boat than the one that's not moving. Its little bits are moving. Its protons are moving. Its electrons are moving in a direction because of their disposition, because of the force complement in their boat, their rowers. So there's a real change. There's a real difference between the two wrenches that can be seen if we could break them open and look inside. We'd be able to see, oh yeah, these are all rowers going this way in this boat, and this other boat, they're not going that way. But anyway, so, and the electron does the same thing in the sense that you get your reflection, which is the exchange, and because you exchanged, you change this thing's net, okay, its net velocity, it's where it's going, the direction of its momentum is now altered a little bit, spread over the entire complement in the boat. This little extra bit of momentum in this direction will mean it'll have some change in its vector. If it was going this way, it'll go this way. If it was going that way, it'll go this way, that kind of thing. It will be oriented more to going in this direction because the net will change. The net of the rowers, the average rower. When you do the math of all the rowers, you get a net vector. The net vector changes. All right, that's easy enough, I think. All right. Next. Let's see. Let's scroll up a little further. Okay. When they interact with matter bits, they are either deflected, as explained. The proton deflects the black stuff, the electron deflects the red stuff. So understand the force has two identities. So the stuff moving the speed of light is either this or this. Okay, and it matters when it hits an electron or a proton. An inverse reaction will happen when it hits, depending on which one it hits. And that gives you the capacity to create magnetism and all kinds of stuff. So can't do it without this relationship existing, realistically. Okay, deflected with no change in momentum, or they reflect, causing an equal and opposite reaction and a change in the net momentum of the matter. So you have the equal but opposite, it's this little bit. The universe sees the change, and this little bit of momentum is just a consequence of what the history of this bit was. So whatever its history was, whatever it had as its current moment, it could be going this way, then it's only going to be changed a little bit in its direction. Because it has to be spread over the entire, whatever new direction it adds, it has to be spread over all the rowers. In the sense you have to essentially move all the seats in the boat. So any bit in here has to move all of these rowers. That's why this moves slow. This was moving the speed of light. This is going to go a tiny percentage of that. Okay, most of the time. All right, so this is another answer to, oops, we're already at charge here. Okay, so what is charge? So charge is the electron and the proton, obviously, and the fact that they manifest these two different field effects. So when you put a charge in the field, all right, now I've just pointed out how the field has this, it has these two forces in it. The whole universe is full of this, always heading right for everybody. So every electron and proton in the universe has this stuff heading right for it. So just imagine these lines going everywhere, from everywhere, in all three dimensions. And that's the field the electron or proton lives in. And what happens is if this is an electron, we'll make it an electron. We just pointed out that the black stuff is going to reflect, so we know that all these black things, let's just pretend this is the reflection side. So this is the side where we're showing what goes in. This is the side where we'll show what comes out. So we know that all the black stuff's going to reflect, right? And the red stuff is going to get diverted. So it's going to look like a reflection. So when it's left alone, I mean, when it's all sort of by itself, you could sit there and say, well, that's the same. What went in is what comes out, a mixture of black and red. But the key is that when you put another one of these electrons in the picture, now we can almost make them down here. Okay, you put another one of these electrons, you can get the idea that all the black stuff is going to just keep reflecting back and forth, and all the red stuff, okay, isn't going to stay even, because any red stuff that hits this electron is going to go that way. Any one that hits this electron is going to go that way, or in or out. And so there won't be any red stuff here at all. And there'll be a bunch of black stuff. So you'll have all black, mostly, and very little of the red stuff. And the black stuff is going to be reflecting. That is, it's going to be bouncing back and forth. And the closer the electron gets, the more interactions there are, the more times the exchanges are made. So you can understand the exchange rate goes up as the proximity goes up. And as pointed out, the exchanges are what's really creating the momentum. So here, when it's making an exchange, it's reflecting right back at the guy. He's throwing a new one at him. So he exchanged, took on a little bit of a momentum change, plus he threw the thing back at a guy who's going to throw it back at him again. So it's coming back again, and it's going to add another hunk of momentum, and it's going to add another hunk of momentum. And it's just going to keep adding these momentum. The closer I get together, the more I'm going to make more exchanges on this side of the electron, right? These two sides are going to be highly exchanging, and these sides are just going to have normal universe exchanges. So you can clearly see why these electrons would be pushed together. So that's the nature of charge. Charge can't mean anything until you put another charge next to it. And if I put a proton, I'll get exactly an opposite effect. See, if I put a proton next to it, well, then we know, well, the red deflects off the black, and the black deflects off the red. So I'm out of luck. I'm not going to have any reflections here at all. I'm not going to have anything enduring. And so this outside pressure is now going to be the strong pressure, and it's going to move the electron into the proton. And the closer I get, the less I'm going to have in here. And this is just an inverse of the same situation. You create a very low pressure here because everything deflects, and you create a very high pressure here because everything reflects. Fits. It makes sense. It's simple. It's the answer. It's the story. That's really how the universe works right there. All right. So it's a manifestation of the difference between electrons and protons. Okay. So I sort of gave you a big piece of that, but anyway. So what are the differences? So electrons divert proton force and reflect electron force. So I'm just pointed out that the basic function is the reflection and then the little piece of momentum, and then if it's red force, not interesting on an electron, and exactly the opposite for the proton. All right. Protons divert the electron force and reflect the proton force. So simple. A field effect caused, so this is the answer to the question, the first question. So it's a field effect. So what's really happening is protons and electrons will reflect back to the universe or give back to the universe a difference. They'll make the universe look different. If you hit an electron, the universe will look different than if you hit a proton. And that's the important thing. What's radiating off of the thing. What goes in comes out. And the fact is, if you hit the electron, a different universe comes out, a different look than if you hit the proton. You can think of it as one goes right through and the other one reflects, and obviously that's going to make a difference in what you see. Okay, caused by the difference in exposure to electron and proton. So as I arrange electrons and protons, I will see the world differently, because you can think of the electron as a mirror to some kind of the energy, and a proton a mirror to the another kind. And so if I mix them up in opposite relationships, I would end up with completely opposite looking, more red and more black, and then a mixture of the two, and blah blah blah. All right, causes opposites to attract and same types to repel. So I sort of already went over that, but obviously the sames is going to be the obvious circumstances, this reflective scenario where you just end up with an intense amount of pressure here, because the same piece of energy keeps interacting because of the reciprocal relationship between these two actions. These two keep making exchanges that end up causing another exchange in the other guy, and so they just multiply the exchanges, and becomes a very strong pressure. All right, creates differences in pressure depending on type. So kind of obvious that, again, if I put the red thing here, the no capacity for this red to go back and forth and back and forth. It just can't happen. It goes this way, gets deflected. Just there's just no opportunity for a magnified reflection. All right, and so creates difference in pressure depending on type. Yeah, it's a pretty straightforward statement. All right, well, maybe I'll take another break just for the fun of it, because I can. Yes, that's why I'll do it, because I can. All right, we're back. I guess I could have erased this previous, but I didn't do it. So I'm sorry for my laziness. So on to magnetism. So it's sort of simple. Okay, another field effect. It's not the effect is what happens to the field. That's all that really matters, is what are you reflecting to the world. So the magnet is really just saying, okay, when this is by itself, one kind of reflection happens through the world, but when I take both of them and put them close to each other, I create what's called a dipole. Okay, and that's a magnet. So any place I have an electron and a proton in relationship to each other, I essentially have a little magnet there. And the point could be argued that in some atoms, this magnet is undone in terms of its meaning, because you essentially create another magnet this way. Okay, so you have a magnet going one way and a magnet going the other opposite way, and the two magnets essentially undo each other. By being in by having exactly the opposite effect, and the net effect is no effect, because whatever this does, this is doing the opposite in terms of its up-down relationship. All right, so let's read the definition of field effect. That is a manifestation of charge. So it's a manifestation of protons and electrons existing and having these two different properties. Charge caused by creating atomic dipoles, bringing opposite charges closer together. So when you bring two different charges close together, you have dipolarity, in the sense, if you're looking at it from this point of view, right? If your eyeball's looking this way, okay, it's going to see, if your eyeball was negative, okay, electron bias, it's going to see the reflections. And obviously from this point of view, and having the same the same uh, orientation, using the same test charge. I mean, I just didn't want to use the word test charge, but looking with the same eye, you'll just see the deflections. You won't see any reflections, so you don't see anything. So one side is relevant, one side is irrelevant based on what charge you put in here. Will tell you what your view is, and obviously from some mixed view, from over here, you're going to see a little bit more of this and less of this. So you're going to see a different amount of what is this net thing. So the net thing changes depending on your perspective. So from different points of view, what this looks like as a net object changes. But that's the nature of a magnet. So if the point is if I use another magnet instead of a charge to detect the polarity, then I can really see the dipolarity, because if I have my other magnet in the same orientation or a different orientation, that is, I reverse the orientation, I'm obviously going to get this effect where, all of the electron radiation, remember, each one of these objects is reflecting the universe. So each one, the universe comes in, okay, the field, and it reflects a copy of it right back at it. And we're just talking about what gets reflected. And so obviously on this side, all the reflections are going to get, drew that the wrong color. All the black stuff will be deflected, and all the red stuff will be deflected. And on this side, the same thing's going to happen. So there's very low pressure. And obviously, if I did the exact same orientation, I would maximize the reflections. All the black energy's trapped here. All the red energy ends up trapped here, and I get very strong repulsion. The closer I get, the more it repels. Exactly like a magnet. It fits perfectly. It'll fit all of the R rules. In this case, for magnets, it's R cubed. It diminishes quickly, meaning that you're dividing the force by a bigger number, not R squared, RR. So this is a much bigger number you're dividing the force by in terms of the way it spreads, and that's because there are lots of locations where the further away you get, the more these two forces, that is, the more black energy, because it's coming out as rays, mixes with the red energy, right? And so you end up with a much weaker field at a distance because there's much more mixture. I'm getting hit by more of one than the other. So the further away I get, the more this just turns into a pure mixture of red and black, and I don't get any effect that's noticeable. So, yeah, that's, don't need to say much more, right? That's just an obvious consequence of charge. So if I could make two perfect charges, balloons. The thing to understand is when we say the word charge, something's charged, especially with static charge, we're usually just talking about a surface charge. So the charge is only on the atoms on the surface. So it's very thin in terms of the things creating it. It's not being created by the stuff on the inside, isn't all radiating this stuff. It's just these surface atoms that are radiating it. So it's a little bit thin and weak in the sense that the charge doesn't have any beef to it in terms of its thickness here. But at a high voltage here, okay, it can have a lot of effect in the sense that you are radiating from each one of these surfaces in this, the same kind of rules where it's spreading from each location on the surface. But anyway, if you could take it, so it essentially looks like an electron. It's not really acting like an electron, but it looks like an electron from all the meaningfuls. By all the meaningful standards, it looks like an electron, and I can charge another thing positive, and so it'll look like a proton. And if I could theoretically take those two things that had static charge, and the static charge is very high. You have to understand to have any real effect, you have to have like thousands or hundreds of thousands of volts on it. So it's a very strong charge. And so the point is, I can never really bring those two close together without them discharging. and neutralizing the charge. But if I could stick them really close together, you can understand that that thing as a thing, so these two balloons with high charge difference would essentially act just like electrons and protons and would become a dipole, and I could detect them with another dipole. By putting another dipole in the field, I could definitely force it to turn, for this to repel, and then this going this, this way. Well, they would just attract, but magnets turn, so if I had it the opposite way, just pretend I did it the opposite way. Right? You can understand why this would turn to reorient itself the same orientation as this magnet, to maximize the low pressure, because that's what it seeks, is an absence of pressure. That's where it'll go. If somebody creates less pressure over here, if they change the field on this side of me and there's less pressure, that's where I'm going. So everything moves based on the pressure. The pressure is what's moving. The field moves everything. The field decides. Everything goes where the field tells it to, essentially. So yes, the electron and the proton are the magnetic monopoles. Whenever that term is used, they fit the definition perfectly. They have the same attributes, and in the sense that they reflect or divert the energy, they're doing exactly the same thing as what big charges would do, if you could theoretically get them close enough. If you could put enough charge on them to notice the effect, and then put them close to each other. But we can't do that in normal atmosphere. But if you did, you can certainly simulate it enough. You can actually take the two charged objects and put an insulator between them, put them close enough together, and then you could take two more charged objects just the same way, and they would behave just like magnets. So there's absolutely just no reason not to understand that the proton and the electron are the origins of the atomic atom. So we'll get to the atom now. So the key is that these two things, when they're in relationship to each other, the proton and the electron, the consequence is, this is the electron, thank you. The consequence is that they have a relationship that means a certain thing. And then what it means is that when the black energy goes into the proton, it will reflect towards, eventually, the electron end. And it will become part of what the electron excretes as momentum. And likewise with the red energy. So when they're in relationship, instead of this energy going out this way or that way, it physically does. But once you put these things in relationship, that is, you stagger a bunch of magnets, these atoms inside of an atomic substance. The argument is that this will tend, this direction that this diversion happens in will tend, over time and probability to cause all of the red energy to eventually come out red ends, and all of the black energy to come out the black end. So you're just really talking about, like, this is sort of a right-hand rule argument, but if black energy comes in here, it ends up coming out here. And the argument is because no matter which way it goes, if it goes down, it ends up reflecting off of another electron, so it goes back up, and then it can turn this way. If it turns this way, it hits another electron, goes back this way. The only way out is always going to be up. That's the only direction the momentum, the force can go. So once I've surrounded this electron, and it would be surrounded by protons. So you can understand, if you have a matrix of these, they have to be oppositely ordered. That is, this magnet has to be staggered to this magnet. All right? And it essentially means that on all three sides of this electron, all four sides essentially, but anyway, because there's going to be another red thing here, there's the same red stuff, and the tendency is going to be, since these are the solid ones here. These are the ones in relationship. They're the atoms that it will come out here in terms of the momentum. So the momentum will go this way. This electron will move this way, and that will encroach in the system and cause all of them to shift their position, and that's why the whole thing moves. That's why the magnets actually physically move. So it's just important to understand that. So when you break a magnet, it breaks on this line. All right, and ends up being, the line ends up being, yes, this is all red, you can see. So it breaks on this line, then this would be the red side, and this would be the black side. And this one would break on the opposite line, which is, it would break all black. You can see this one would break off, and everything would look black when you look down at it. And everything would look red when you look up at this end. And that's the formation of a magnet. So you take a bunch of atomic dipoles, stagger them in the material, and you'll create all the red energy that comes in the one side. I mean, I'll draw it, but it's, you know, it's sort of rudimentary, and if you've paid any attention, you've already seen this. But you can get the idea. You know, that, so all the black stuff that comes in here, it's going to reflect. So all this side is going to reflect as black from the black, and any black that comes in here goes out this way, and so it's going to end up coming out here also. So that adds black force to your black reflection. So, and the exact opposite's happening on the red end, so it's all red on this end. It's never all, so I'm just using this as a, obviously it just has a bias in that perspective. So no magnets are perfect, so there's always red leaking out of a normal magnet. There'll be a little bit of extra in here that's polluting it a little bit, but the point is it'll be 80%, you know, black, and this will be 80% red, and blah blah blah. But that's the nature of the beast, and it's made out of this premise, this fundamental, easy to see observation that all the magnet really is the electron and the proton. And it's just a bigger manifestation of what happens when you stack a bunch of electrons and protons on top of each other. It's really quite simple. All right, bringing opposite charges closer together. So what is an atomic dipole? An atom that from some point of view provides more exposure to electrons than protons, or vice versa. So it only has to be, it doesn't have to be a good atom. It can have a lot of atoms. You know, it can have, there can be atoms going this way, you know, electron, proton, you know, just imagine that's red. It can have all kinds of mixtures in it. And the point is from a perspective, what's the net effect? How much is there? Is there really more, just even slightly more black coming down one end than, and a slightly more red coming from the other end? So you know, you have this, I'll just draw it as a 3-to-2 relationship so you can get it, and I'll draw the other arrows a little bit dimmer. So the idea is just understanding there's a disproportion. So from certain points of view, it's going to look differently. So from this point of view, obviously, to a single charge, like an electron, this is going to be a mixture. I'm going to be getting some low pressure from this side. I'm going to get high pressure from this side. Okay, so as I get closer, this side's going to get higher pressure. It's going to say, no, 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 you can't go over here. And this side's low pressure, so I'm going to move in a direction like this, you know. Because I want to get to the high pressure. And those are what they call field lines, but those field lines don't really mean anything. They're just a path that a charge would take. They're not a real line in space of any kind. Where these lines, the force, rays of force, those are the real lines. These lines of force are what creates the reason why this charge will move in these directions. Okay, that's probably enough of that. Yeah, I think so. An atom that from some point of view. So again, it just really has to do with viewpoint. So I've talked about this lots of times. If you so a way of looking at it is that again, I can make analogies to distances. You know, if I have two things and I change their distance, I can change what you see. So especially if protons are bigger than electrons, which is the theory, right? And so electrons are smaller. You can sort of understand that from your point of view, as you got to view it from underneath it somehow, right? Get that right. So from your point of view, I can change what this looks like by merely, if I move this electron closer to you, the electron gets bigger, okay, in terms of it occupies more of your view angle space because it's lower in the, see, your view space is like the opposite of rays, okay? You see a perspective, okay, that's like a ray of perspective. And the more of these little lines, this is pure Maxwell, okay? So I'm not violating any conventional physics here. These are pure rays. And so you're going to intersect more of these ray lines the closer you are, right? The further away you are, look how big that arc is. The same force has to be spread over that bigger distance, so it's a lot thinner. But obviously, if I make this close enough, you won't even see this. That's gone. You can't see it because this is blocking the angles. Okay, so you're not in the angle you can still see in, which is this peripheral angle. So you're getting nothing from this. So this is going to look like it's very negative, okay, because there's lots of electron. If I do the opposite and I put the electron really close to the proton, you can see that, oh, what am I going to see then? Well, then everything changes, right? Because now, okay, your view angle is tiny for the electron. It's only this little tiny angle. You know, this, you can't even draw it. It's such a small little angle. And there's lots to see here from the proton, lots of red. So now this looks real positive. So just by moving this electron, I change what I see. That is what gets radiated to me. The radiation that hits me is going to be different. If the electron's here, I'm getting more black. If the electron's here, I'm getting more red. Okay, so you can sort of see that. I see proton when it's here. I see electron when it's here. And that's essentially polarity. So you can think of the polarity of an atom just being how far away is the electrons. You know, how far away from the atom, the proton are they? So if I make the electrons further away, I make this into a negative atom. I make the electrons close to the proton, I make it into a positive atom. And that's a form of ionization, or a form of polarizing an atom. And I would argue this is what causes electricity, which I didn't define in this group. But this is what's happening, is that in electricity, all you're really doing is, you know, expanding and contracting protons and electrons. So you're just changing the size essentially of the atom. So the neutral atom has this as the distance, and then it's right next to another atom, okay, that has this at the distance. Okay, a little circle. And what's going to happen is this electron and this electron are going to share their pressure because they're going to encounter each other. And you're going to end up with two atoms that are going to be neither of this size. You're going to end up with two atoms that are going to change to be half of whatever that is, the average of those two sizes. Okay, so that's the transmission of the pressure. Now, if I keep pressurizing the atoms next to this one, okay, if I keep pushing expansion pressure into this atom, then that chain of transfer is going to keep happening. If I stop pushing pressure, that is, I stop pushing in pressure that pushes the electron further away from the proton, then this will stop, this chain reaction. But that's electricity moving through a conductor. So that's a little bit of free bonus. All right. And so on to gravity. All right. So gravity, let's understand, is an effect. So this is, another. You gotta keep pointing out what's an effect and what's a cause. So gravity is an effect. It's not a force in and of itself. The forces should be called something else, the universal pressure. And all gravity is where there's an imbalance in that pressure, then we say gravity's happening. So gravity's happening to me now. I'm being pushed into the earth. I'm denting my chair. But a Chinaman's doing exactly the opposite. So we're both pushing stuff into the earth in opposite directions, effectively. And that's a real event. It did not happen. And by doing that, I'm making matter move. And the only way it can move is it has to do this exchange thing has to happen to change its direction. So a bunch of exchanges are happening in that direction from me, and the Chinaman's doing exactly the opposite. And that effect is, the net effect of that is that I'm getting hit by less force coming at me, from below than I am force hitting me from the head, and I'm sinking into the earth. I'm being forced, I'm being pushed by the field into the earth. And that's all that's happening. All right, caused by imbalancing pressure-force distribution. So the force is essentially pressure, so those two words can be interchangeable. And again, lots of other words can be interchangeable, like trap and absorb and delay. Those are all words that can be interchanged. So let's just understand that too. Caused by imbalancing pressure-force distribution. So all you're saying is there's two objects here in the universe, and gravity is going to be a consequence of the fact that this thing is going to change the environment here. All right? It really can't change the environment out here, so it can't change what I see from this part of the universe, but it's going to change what I'm going to see from this part of the universe. And so as that happens, the argument being made simply is that as I move this way, okay, I'll absorb the force this way that would have hit this other object, and he's doing the exact opposite. Okay, there's force that would have hit me, but this thing is in the way, and it's going to absorb that force. The boat jumper is going to jump in the boat, the other opposite reaction. So that's going to happen, and I'm not going to get hit by a force I should have been. That would have given me a balanced view of the universe. So I'm not going to see a balanced view anymore. I'm going to see this imbalanced view. And it's going to move these two objects. Are going to keep moving into each other. And that's basically gravity. All right, so what causes the imbalance? Force, pressure is trapped, delayed, absorbed. So those three words are essentially the same, and becomes imbalanced. So there's pressure in the universe. Like I said, if I put one thing in here, there's stuff. Okay, there's a universe, and it's all equal. And if I put something else here, I've unequalized this section of the universe. Okay, this section of the universe now isn't equal because this thing is factually in the way, and as a fact consequence, this now, his perspective of the universe is going to be changed because this thing is in the way. And being in the way matters, is the simple answer. All right. The momentum has to come from somewhere, so any movement in this direction is an absorption of force in this direction. And this moves much slower again. So the force, when it's trapped, okay, when the force is trapped and traps, and when it's trapped, going in useless circles or back and forth, it's not going anywhere. It's not getting where it was going. And that delay is real, and it has a real consequence on the rest of the stuff in the universe. All right. How is the force trapped or delayed? So the trap is, again, the electron and the proton. And their movement is an evidence of when something has been trapped. So you want evidence of what's been trapped, you just see where's the electron going. Okay, if the electron's going this way, it means it's trapped energy. essentially going that way. That means it's a trapped energy going this way, and some energy going that way, and some energy going this way, and some energy going that way. And it equals, when you add up all these vectors, it equals this way, or this way. So that's what it's trapped out of the universe, is a bias in this direction overall. When you add them all up, when you add up all the stuff that's trapped in here, it points this way, and that's why the electron's moving that way at some velocity. And its velocity just represents how much of a bias it's trapped. So how much stuff that was going essentially in some form of this direction, you know, that way versus that way, in that 9-degree hunk, how much is it absorbed going that way? And, you know, it's obviously, if it's got velocity, it means it absorbed it. That means all of this energy didn't get where it was going at the speed of light, and instead is moving much slower. Now, when this finally shows up over here and hits it, okay, the brick wall or something, you'll see all of this stuff that was trapped, because there's going to be a huge problem, because all of a sudden all this stuff is going to be accelerated in one direction, and it's not going to be able to do it fast enough. And you're going to see bits flying all over the place, because everything's going to start breaking. All right. Scroll a little bit. So it is used occupied, moving electrons and protons, and eventually the atoms, of course. So the whole point is when this thing's moving or gaining acceleration, changing its speed, and it's gaining more speed in this direction, that means it had to absorb a force. So if something didn't, if I didn't shoot it with a gun or a bullet, then it has to absorb energy from the field, energy that would have gotten over here, and you know, so I've absorbed it, I've occupied it, I'm delaying it by keeping it in the proton and forcing it to move all the other stuff in that proton or electron. And that's what's delaying its arrival. And by delaying its arrival, I'm essentially saying it didn't arrive for a whole period of time that it was supposed to. And so this thing has no choice but to fall into the low pressure created. It has to move into that low pressure, because it's going to make more exchanges going this way, you know, and it's going to be making less exchanges going this way. And the consequence of that is the boat is going to end up with a bias in this direction. It really is so simple. All right. How does it move electrons and protons? Well, I just explained that, right? I mean, it's the boat. It's the simple mechanism. It just simply says, okay, if I got a boat and I got seats in the boat, and I put, you know, I have 5 interactions going this way, okay, all those interactions mean somebody left the boat going that way. So 5 boat rowers leave going that way, and I put 5 new ones in here going this way. All right, and if I only have 3 doing it this side, I only have 3 interactions there. Obviously, there's going to be a change in my velocity, because now I got 5 to 3 as the change. And if I was 4 to 1, you just do the math and you figure out, well, I'm going to be moving faster in this direction. Just no way to avoid it, because I've got the rowers. They're in the boat. So that's how electrons and protons move. And when electrons and protons move, the atom obviously moves. All right, the bits of the force make a reciprocal change with the force bits in the electron-proton. See the boat analogy. So, you know, I've sort of explained the boat analogy. The boat is just holding force. It's just holding locations that these things, these bits, these swimmers can sit in. Okay, and the point is the seats are already occupied. They kick out the occupant, and the occupant's going in the opposite direction, and so therefore the boat moves in a direction instead of just spinning in circles. Okay. How do these exchanges create imbalance? Reasonable question. When any 2 sides of an electron experience a difference in force pressure, that is, when this side has more stuff than this side, the electron will absorb, trap more force in the direction of the higher pressure. Obviously, more interactions this way, less interactions this way, more exchanges this way, less exchanges that way. Too simple. Trap more force in the direction of the higher pressure is moving. So there's going to be more traps that this stuff is falling into than traps this stuff is falling into. And therefore the thing's going to move in the direction of the higher pressure. Well, that's exactly what I say. Trap more force in the direction of the higher pressure is moving, in turn lowering the pressure passed to the universe. So all of these guys jumping in the boat, now moving much slower, means these extra guys here didn't get where they were going. These two extra didn't get here to smack something and create balance in their field. Now their field is imbalanced and they have to move into the imbalance. When they move into the imbalance, they're absorbing stuff that would have gone this way, and now you're just amplifying the cycle of imbalance. Now the gravity we're in, as stated, is caused by the fact that the inside of the earth is constantly moving. Just like right inside of me now, there's stuff going this way and there's stuff going that way right now. And all that stuff has to keep, this momentum has to constantly be fed. You can't move for free, because as you move into the field, that means you're moving into more swimmers, and those more swimmers will obviously create more exchanges, and so your velocity will be killed. So for the velocity to be maintained, there has to be a constant source of new swimmers to feed it. So as the center of the earth is moving, the jello, the hot stuff is swirling about and moving about. It's moving in both directions all the time. And that movement is absorption. So all the time it's absorbing energy that was going somewhere and it's not going to get there. So when this part of the crap is moving this way, then it's absorbing the energy that for this guy out here, is saying, well, all of that mass inside the earth moving in this direction has absorbed force that would have hit me. It's not hitting me, so I fall into the low pressure. And the same thing's happening for the force going the opposite way. And they're both just complementing each other and causing so you fall into gravity you're not really creating. You're causing more motion. You cause more motion to happen inside the earth, but it's not the motion you're causing that you fall into. The gravity that's affecting you is the gravity of the ground below me. That's absorbed the energy by pushing up, by pushing back at me. The earth, it's demonstrating the fact that I absorbed energy to push you back, and it absorbed the energy that I would have fallen into. So it's the ground below me that it's the gravity being caused by it that is attracting me. I'm going to create gravity that something else will fall into, because I'm adding to the mass of the earth, and I'm adding to the stuff moving this way and the stuff moving that way. But this way doesn't matter to somebody out here. What's getting absorbed going this way doesn't matter too much to somebody out here. He's more concerned about what was supposed to get to him. And the absence of that reflection means that you can't have the reflection. You can't, even though this would be a reflection, there's two objects here. One would, well, I should draw it. Now, I don't know if it's a point that needs to be made, but if you prevent a reflection, obviously you can't have a reflection. So when this object is here, this object's here, and this object absorbs the energy, well, you could argue that, again, when that happens, that means something left the universe going this way, and the same thing would happen here. But the fact is because this little bit of energy never got here, okay, it got absorbed in here. It should have been here, right? So that's the argument. It's delayed in here, this arrow, so it didn't get to me. And so now it can't reflect off of me and hit him again to push him away. You get it? So the consequence of blocking this arrow isn't just that you blocked one arrow and one exchange. You blocked the reflection that would have pushed this guy away. So that's the key to it. By blocking it here, you stopped the reflection. And that's why gravity is functional. But it's it's just kind of a subtle point you really don't need to understand. To understand the basic concept is if you see something moves, it moves for a reason. And to move, it has to be absorbing energy to keep moving, and unless it has a mechanism. So the key, see, that's another velocity point. This object doesn't move just based on an imbalance in the force that exists around it. It moves because of its previous momentum, what it's stored. And because the atom can have stored in it energy in directions, that is, it can have a relationship between protons and electrons that create this circumstance where there's a perpetual reflection, that is, a diversion and a reflection through a proton. It means that this is like a little motor, and will keep pumping this atom or this nuclei in that direction. So you can gain velocity. So you don't accelerate like 10 meters per second. You don't accelerate and just move that speed. You move that speed is how much force is pushing on you, and that adds by creating these little engines to your velocity. So your total velocity ends up being some percentage of that added every second. So in the first second you might go 8 miles an hour, or 8 meters a second, 8 meters per second velocity, and then you'll get up to 16 after the next 10. So you don't absorb all of this as velocity. That means that in converting your acceleration, that is how much force is hitting, in converting it into these little orientations of neutrons, that doesn't happen with perfect efficiency. So you don't get your full 10 meters per second and get to add it. You only get a part of it. And so where you'd say in 3 seconds I should be going 30 miles an hour if this was miles an hour instead of meters, you won't be. You'll be going 22 instead, because of the inefficiency of turning acceleration into velocity. Because to turn acceleration into velocity, that really means you have to create these little motors in the matter. Little nuclei all have to be turned a little bit to have these electrons and protons. These are really the neutron. This is the neutron and an extra electron. But anyway, it doesn't matter. And connected to another proton. But anyway, that's more detail than you really need. But it just is a way of understanding that velocity and acceleration aren't the same thing, and that acceleration is where you're absorbing the force. So your acceleration is what's causing this imbalance. Your previous velocity is something you brought to this new field location. So when you move into a field, your previous velocity, okay, say I'm going 500 miles an hour here, okay, really, and I move into a new location, I'm taking 500 miles an hour worth of force from over here somewhere. Somewhere else in the universe is where I absorbed the energy. I accelerated somewhere else. Okay, so my acceleration happens somewhere else, and I'm bringing that bias into this new part of the universe here, this new section. Okay, but I absorb the energy. I could be a million miles away where I absorb the actual momentum, where I absorb the force. It can be a long time ago. It doesn't have to be yesterday or a second ago or any of that stuff. I could have trapped it a long time ago. The bias. And so I'm just bringing a bias I created in some other part of the universe. In some other part of the universe I created a bias where there's less arrows going this way because I took them and moved them here. Obviously in a sense I took them and robbed this part of the universe from them because they would have been already here a long time ago, so I delayed them is probably the better way to say it. I'm bringing them, it's a belated gift or something. Well, anyway, detail you don't need. So that's the basics of it. So there are a couple of words, ray and wave, that maybe I'll deal with next, in terms of understanding why this really has to be understood as rays. Rays are what's in Maxwell's drawings. It's just a fact. It's what makes Einstein's bent space make any sense at all, is rays. They're straight line, discrete vectors. The universe doesn't function. Photons aren't. A single photon is not some wave going all over the place. It's going in one direction, and there's about 1 million experiments that demonstrate that. It just doesn't make any sense to think of some wave that just stays in one place. This is not it's called this. I mean, a wave does this, okay? A wave creates this and this. Like an ocean, I poke the water and the wave is created in all directions. That's not what this electromagnetic radiation is. Just this. It's not moving in any. You don't call this a wave. No, that's crazy. That's a ray. This is a wave. This crap. That's not what a photon is. Okay, so till the next time and such. It's not what a photon does. It's just silly to say photons go everywhere and they only land in one place, even when they don't go through a slit. Somehow it's a wave of photon that went everywhere. Well, it doesn't go everywhere. It lands in one single location. I mean, it's just nonsense. All right. It doesn't make any sense. I don't want to be insulting. I'm just saying it just doesn't make any sense to say you have a ray that's a laser beam ray. Doesn't make any sense. All right. So, till next time and such. Again, I can only provide you good reason, to believe something reasonable. I think I've given you good reasons to accept a reasonable theory of physics instead of this wooey, bent stuff, virtual stuff, entangled stuff, all of this mush that you just don't need. All right. I mean, really, all I can do is I can point out A, B, C, D. I mean, a rational order of the letters. You want to keep looking at them crooked, I can't help you.